All right, time to get started. So let's get rolling. Okay, before I begin, there's been some questions coming about final exam sign up because you guys are all, finely tuned robots at this point that expect to be able to sign up for the exam exactly 2 weeks before it happens. For the final exam, that's not quite right. So the final exam sign up will start on April 26th, which is just 1 week before the exam. All right, so if you're trying to sign up already 2 weeks in advance, you won't be able to just yet. So April 26th is supposedly the date that it opens. Again, I don't have direct control over that, so don't get mad at me if that's not the case, but it should be the case, is what I've heard. And then what I have confirmed is that the dates for the final exam are exactly what they're listed on the syllabus, May 3rd through 6th. All right, so we are a little bit at the mercy of CASA for scheduling these things, but I've confirmed with CASA that those will be the dates that you're actually taking the exam, and if everything goes as planned, you'll be able to sign up for that starting next week. All right, so it's a little bit more spread out. It does include the 6th, which is the Saturday, so be aware of that, but you'll be able to sign up for times just like you normally do for any other exam. Okay, so what we're going to do today is go back to liquids and talk about a phenomenon called vapor pressure, which we've already introduced on a very basic level, and we're going to see more details about that. But before we get into that, let's review a little bit of what we did last time and give you an idea of some of the types of problems we could give you related to that material. So last time we talked about the structures of ionic compounds, and the idea being that one of the ions, typically the larger one, is going to occupy one of the lattice positions that we've already talked about. We're going to deal with cubic lattices exclusively in this case. So you're going to have ions that are occupying either a face-centered or a simple cubic lattice, and then the oppositely charged ion, typically the smaller one, is going to be filling holes in that lattice. And we define the different types of holes and classified them, and there's 3 that we need to be familiar with. All right, so once again, I gave you a lot of details last time that were geared towards helping you understand this stuff, but really if you know the information on this table, that should allow you to approach the vast majority of the problems we would give you on these topics. All right, so as we saw, the number of holes per unit cell. Now this is the net number of ions that can occupy those holes. So for tetrahedral holes, we have 8 holes, and all of them are completely inside the unit cell. So there's a maximum of 8 ions that can reside in tetrahedral holes for a given structure. Octahedral holes are a little bit different because in this case we have 1 in the center that counts fully as 1, but then the rest of the octahedral holes are all along the edges of the cube, which only count as 1/4. So when we add up all of those, in net we have 4 ions that can reside on octahedral holes, or in octahedral holes. And then finally, cubic holes is a pretty simple one because it's a simple cube, there's a hole in the middle, you put 1 in there, so that just counts as 1, obviously. Alright, so that's the number of ions that can reside in each of those types of holes. The other thing that's important is the relative size of the smaller ions. So if we want to predict which holes is an ion going to go into, it depends on the relative size of the small ion to the big ion. So the small ion, remember we abbreviate that with lowercase r, and then if it's between 0.225 times the radius of the big ion all the way to 0.414, we would predict that it's going to go into a tetrahedral hole. Now these guidelines are not perfect, so there are structures that sort of violate this expectation, but if you were asked to predict which hole are filled, you're going to use these radius cutoffs as sort of your guiding point. For octahedral holes, those are a little bit bigger, so if the radius is between 0.414 times the larger radius all the way to 0.732, we would predict that the ions would have to go into the octahedral holes, which have a little bit more space. And then finally, cubic holes are the largest ones, and this would be anything bigger than that. So anything bigger than 0.732, we would expect it to go into a cubic hole. Now, as I said, these holes exist in one of the regular cubic structures that we've already talked about. So octahedral and tetrahedral holes are in the face-centered cubic lattice that we discussed earlier. Cubic holes, the parent lattice is the primitive cubic. All right, so we don't have, at least any that we're going to talk about, any common ionic structures that derive from body-centered cubic. It's either face-centered cubic or primitive cubic that gives rise to these types of holes that we can build ionic structures from. All right, so with that as a little bit of a review, let's look at a couple of problems. So as we talked about last time, the idea here is we're going to fill the holes, and we need to make sure we fill the correct number of holes such that the stoichiometry of the ionic compound works out. So if we have calcium fluoride and the cations occupy a face-centered cubic array, if we're going to fill the anions into tetrahedral holes, how many of the tetrahedral holes must be filled? All right, so last time we saw a structure zinc sulfide which had half of the tetrahedral holes filled. Let's figure out how many holes are filled when we have calcium fluoride. So the first thing we need, of course, is the formula for the ionic compound. Calcium is 2 plus. Fluorine is F minus from the periodic table. So the correct charge balance formula is CaF2. So that should be a review, just how to find the formula for that. And then from there, we're going to figure out, okay, if we have our calcium ions are in a face-centered cubic array, let's figure out how many of those there are. So remember that in face-centered cubic, this was in the the table, the summary table that I gave you before for the lattices. But these are going to be on the FCC positions, face-centered cubic positions. Remember, we have 8 corners in a face-centered cubic lattice that are all filled, and those count as 1/8. We have 6 faces in a face-centered cubic. Those count as 1/2 because they're shared between 2 unit cells. So remember, in total, this also is a review, we have 4 ions or atoms that can occupy a face-centered cubic lattice. So in our unit cell, we have 4 calcium 2 plus ions. We need to have we need 8 F minuses because we want to have, again, the formula is CaF2, the empirical formula is CaF2, so we're going to have calcium 4 F8, which is going to be equivalent to calcium F2. So if we need 8 fluorides, remember that the number of tetrahedral holes maximum that is going to be 8. So that means we need to fill all 8 of those tetrahedral holes to make this structure. All right, so when it's a 1-to-2 salt, where you have, in this case, 1 cation and 2 anions, the cations are on the face-centered cubic position. There's going to be 4 of them. The anions, if they occupy tetrahedral holes, we have to occupy all 8 of them to have the correct balance of cation to anion. All right, so that's one type of question we get asked. And then another one here, which is a little bit more out there, I guess, is a sort of a non-standard situation. So we have a compound called lithium boride. Now it can be classified as an ionic compound, or it's kind of in between, right? Because boron we know is a metalloid. Go back to the periodic table. So this is kind of a weird compound. We're not going to worry about these details, but just to orient you a little bit. Boron's here. It's a metalloid, so it can sort of have metal and non-metal properties. So if you combine boron with lithium, we can make a compound called lithium boride, which could be either thought of as an ionic compound with lithium cations and boride anions, or it could be thought of as what we call an intermetallic, which is 2 metals mixed together into a regular structure, kind of like an alloy. So how do we classify the compound? It consists of lithium and boron, and we're saying here that the boron occupies the face-centered cubic lattice, and the lithium occupies all of the octahedral and tetrahedral holes. So we want to know what's the formula for this. So we have to count the atoms for each of these. All right, so for boron, we say that they're going to occupy the face-centered cubic. So we have 4 borons in the structure. Remember, if we occupy all the positions for face-centered cubic, that's a net of 4, as we talked about in the last one. And then for lithium, we're occupying both octahedral and tetrahedral holes. So this is not a common situation, but there are cases where both holes are occupied at the same time. And so we have, remember, we have 4 octahedral holes, we have 8 tetrahedral holes. So we're going to have a total of 12 lithiums. All right, so in total, our formula is Li12B4, which reduces down to Li3B. All right, so the formula for lithium boride is Li3B, which means if we treat it as an ionic compound, boron has a 3- charge, which is not something we would easily predict from the periodic table necessarily. But by looking at the structure of the compound, which positions are filled by the boron, which positions are filled by the lithium, we can just count the atoms and get the formula that way. All right, so these are the kinds of problems you're going to be able to do. If you know how to count the different holes and sort of some of the major differences between them, you'll be able to do most of these things. All right, any questions on that before I move on to the new stuff? All right, so the new stuff is going to be dealing with going back to liquids. So we've talked a lot of details about different types of solids. Now we're going back to liquids. Another property of liquids is vapor pressure. And we want to first understand what it means, what vaporization is. So vaporization is the process of converting a liquid into a gas. All right, so it's a phase change. We're going to close up on Friday with even more information about phase changes, but this is one of the phase changes, which is converting a liquid to a gas. And something else we'll see in more detail as we go through today and on Friday is that every phase change has an enthalpy associated with it. So if we were to take 1 mole of certain liquid and convert it into 1 mole of that gas, there's going to be an enthalpy change that we call delta H of vaporization, abbreviated like so, enthalpy of vaporization. So it's the enthalpy change associated with vaporizing 1 mole of a substance. All right, we know intuitively that we have to put energy into something to vaporize it. If you want to boil water, you have to heat it up, of course. So that would mean it's an endothermic process. All right, so in order to vaporize something, we have to put energy in. It's always going to be endothermic, which means it will always have a positive value. So that means the sign will always be positive. The reverse of vaporization is called condensation. So that's when we take the gas and revert it back to the liquid phase. All right, so you've certainly seen condensation before. If you take out a glass of ice water on a warm, humid day, you'll see condensation forming on that. Or if you're boiling water and you put a lid on it, you'll see condensation on the lid, which is not as warm and all that stuff. So you've seen condensation before, it's just the opposite process. This also has an enthalpy change associated with it, but as we know from the property of delta H, if condensation is just the reverse process of vaporization, then the sign is just going to be the opposite. It's going to be the same magnitude, opposite sign. All right, so condensation enthalpies are going to be negative. We're not really going to deal with those very often, but if you wanted to calculate the enthalpy associated with condensing a gas, it's just going to be the opposite and the negative of the delta H of vaporization, because it's completely the reverse process. If we reverse a reaction, we reverse the sign of delta H or change the sign of delta H. All right, so with that in mind, we can now talk about what causes vapor pressure, because we dealt with vapor pressure way back in chapter 7 is when it started, when we were, or sorry, chapter 8 I think it was, when we talked about gases. So we have those problems in chapter 8 where we collect a gas over water, and we talk about how the total pressure is really the sum of the gas pressure and the water vapor pressure. So why is there this water vapor pressure always above liquid water, or why is there vapor pressure above any liquid that we have? So let's try to understand how this happens sort of physically. So when if we want to measure vapor pressure, if we want to consider what it is, we place a liquid into a closed container. And so at the beginning, everything's in the liquid phase. But then what happens right away is that there's going to be net vaporization. So some of those molecules at the surface of the liquid are going to have enough energy to escape into the gas phase. Now, eventually, it's not going to vaporize continuously, provided you're below the boiling point. So, if you're below the boiling point of the liquid, some of it's going to vaporize, and then eventually you're going to reach a constant pressure. So, eventually, we get to a constant vapor pressure, and that would have been the value of the vapor pressure that we would have used in some of those problems we did in chapter 8, so whatever that constant vapor pressure is for that specific temperature. All right, so the reason that this happens is at the beginning, we're going to show sort of what happens at the beginning versus what happens later on when we've gotten to that constant pressure. At the beginning, everything is in the liquid phase, and in that we have molecules that start escaping from the surface. So early on, the vapor pressure is going to increase as molecules escape the surface, but then after some period of time, you reach what's called an equilibrium. So you're always going to have molecules escaping the surface, but at some period in time, the molecules that are escaping the surface are going to have the same number of molecules that are condensing back in. So you're going to have some gas phase molecules that then recondense. And so you have sort of both processes happening simultaneously, vaporization and condensation, such that at some point in time you're going to get a net vapor pressure where there's no longer net escape of the molecules from the surface. So every molecule that leaves the surface, another one comes back and condenses back into the liquid phase. And you're going to have always some molecules in the gas phase that are exerting a pressure on the walls of the containers. That's why we measure a vapor pressure. Anytime you have molecules of gas moving around in a closed space, they exert pressure, as we've already talked about. So this is kind of what it looks like pictorially, and then we can think of it in terms of a graph. So what I'm going to show here is the rate of vaporization and the rate of condensation as a function of time. So at a given temperature, the vaporization rate is constant. So I'm going to show that in blue, and so your vaporization rate is basically just a straight line, or really it is a straight line, to the extent of my ability to draw one. So the vaporization rate is constant over time. It doesn't change as long as the temperature is the same. But then the condensation rate, which is the opposite process, that's going to increase initially because it depends on how many molecules we have in the gas phase to start with. All right, so our condensation rate increases initially because we're only going to have condensation when there's molecules in the gas phase to condense. As I said at the very beginning, you don't have any vapor molecules in the gas phase, so there's nothing to condense, but over time you get more molecules into the gas phase, and then more of them are going to start condensing, and so the rate of condensation increases. But it's eventually going to get to a steady value that's equal to the vaporization rate, and that's when you get to your stable vapor pressure. So those sort of like this. All right, so the red one again is condensation, which increases initially and eventually is going to be equal to the vaporization rate, and that's when you've gotten to that constant vapor pressure. Now, we're not going to talk about how long that takes. It's typically a fast process for most liquids anyway, but realize that this is sort of the phenomenon that gives rise to vapor pressure, but the reason that the vapor pressure doesn't continually increase is because the rate of vaporization is constant and eventually condensation catches up to it. All right, so let's talk about how we measure vapor pressure now. We use a barometer to do this. We talked about how a barometer is a device that's used to measure the pressure of a gas. Now, barometer is typically used to measure atmospheric pressure, but we can also use a barometer to measure vapor pressure. Okay, so first we use that barometer to measure the atmospheric pressure. Then what we're going to do is we're going to inject a liquid into the top part of the barometer. And that liquid, of course, is going to have a vapor pressure associated with it, which we're going to measure by difference. All right, I couldn't find a good picture of this, so I'm going to attempt to draw one. So what you have initially is your barometer, remember, is sort of like a bowl of mercury. And then it has an inverted tube in it that has the mercury that goes up. All right, so basically what you have is your atmospheric pressure pushes down, remember, and then it forces mercury up the tube. Make that a little bit higher just to exaggerate. So initially, remember that this part of the barometer is under vacuum. There's no pressure in there. And the height of this column at atmospheric pressure is typically going to be around 760 millimeters. Okay? So that's what we're starting at. We measure the atmospheric pressure, which is usually around 760, but we'll get the exact value by measuring the height of the mercury column. And then what we're going to do is we're going to add a liquid to the top part. All right, so this top part of the barometer that's initially under vacuum, we're going to inject a liquid into there. You can inject it in the bottom and it'll float to the top, or you can have a little port in there that you inject it into. And so then what's going to happen in this case is you have the barometer still with the mercury. So you still have your atmospheric pressure that's going to be pushing down and forcing mercury up, but then you also have your vapor pressure that's pushing down on the column in the opposite direction. All right, so your vapor is sort of opposing the force of the atmosphere, so it pushes the column down. And you're going to measure the new height of the column, which we call h. And then what you have is that this height value here, h, is going to be equal to the atmospheric pressure minus the vapor pressure. All right, so that's the difference between the atmospheric and the vapor pressure. So in this case, the atmospheric pressure is a little bit higher, which it is for any liquid below its boiling point. So atmospheric pressure is pushing down and then forcing the mercury up. The vapor is pushing in the opposite direction, and the difference between those two pressures is going to be equal to the height of your column. And that's how we calculate atmospheric pressure. So as an example, let's assume that we have exactly 760 millimeters of mercury as our atmospheric pressure. So if we had water at 25 degrees Celsius, let's say we're doing this at room temperature, and we put water into the top part, we would measure a height of 736 millimeters of mercury. And then the vapor pressure would be 760 millimeters of mercury, which is atmospheric pressure, minus that value 736 that we measure after adding it. So our vapor pressure at this temperature is going to be 24 millimeters of mercury. And that's the number we would have given you in previous problems that deal with this, and that's how we get that number experimentally. We measure it using a barometer or some similar pressure measuring apparatus. All right, that just gives you a little bit of background on how we measure atmospheric pressure and what it is. What we're going to start talking about now, what's going to get us into some of the problems we're going to be able to doing in this section, is the temperature dependence of vapor pressure. So when we first introduced this in Chapter 8, we said that the vapor pressure depends on the temperature, and we left it at that. Let's talk about in more detail what that dependence is. So here's a sort of a graphical representation of what happens. So as I mentioned, when you have a liquid, there's going to be some molecules on the surface that have enough energy to escape. So as we talked about for gas molecules, and the same thing is true in liquid, at a certain temperature, you're going to have a distribution of kinetic energies or velocities, however you want to think about it. So if we put the fraction of molecules on the y-axis, and then the kinetic energy on the x-axis, let's say, there's always going to be a distribution of kinetic energies at a given temperature, just like we have for gas molecules. So at some lower temperature, it's going to look something like this. Let's say this is our cold temperature. And then some of the molecules are going to have enough kinetic energy to escape the surface. So only the molecules that have high enough kinetic energy are able to break free of the intermolecular forces and leave the surface and go into the vapor phase. So let's say that this is the minimum kinetic energy that's necessary to break free from the surface. So some small portion of the molecule is going to have enough kinetic energy to escape. All right, now let's see what happens if we go to a higher temperature. So that's what's true at lower temperature. A small portion of the molecules have enough energy to escape. At the higher temperature, which I'll call the hot temperature, just to be as specific as possible, we're going to have the same axes, fraction of molecules and kinetic energy. Remember that when we raise the temperature, the distribution spreads out. And so our peak is basically going to move to the right, and we're going to have a broader, flatter distribution. So when you raise the temperature, you have more molecules that have the higher kinetic energy. So let's say that's our minimum, and now you have a lot more molecules. A larger portion of the molecules have enough energy to escape. All right, so as you raise the temperature, the average kinetic energy goes up, as we talked about, and so you're going to have more molecules in your sample that have enough energy to escape the surface, and you would expect the vapor pressure to increase. So the conclusion from this sort of molecular point of view is that the vapor pressure increases as the temperature increases. All right, higher vapor pressure correlates with a higher temperature. So now let's start talking about the quantitative dependence of this. So we're not going to derive this equation, but there's an equation for vapor pressure as a function of temperature. So what it looks like is the natural log of the vapor pressure. I think this is the first equation we've done in this course that has natural log associated with it, so make sure you know where that is on your calculator. That's going to be equal to the negative of the vaporization enthalpy minus delta H of vaporization divided by R times 1 over the temperature plus a constant. All right, so this is the vapor pressure, this is the vaporization enthalpy, this is R, the universal gas constant. As we'll see, we'll use it in joules because it's an energy term. This is temperature in Kelvin, and this is some constant. Now this constant here depends on the identity of the substance. And since this depends on the identity of the substance, and since it's not really very well defined for a lot of things, there's a more useful form of the equation that compares the vapor pressure at two different temperatures. So what we do is we measure the vapor pressure at two temperatures, and we relate those two to each other with this equation and sort of solving for the ratio of the two. So instead we look at the natural log of two vapor pressures, P1 over P2 we'll call it. That's equal to delta H of vaporization over R times 1 over T2 minus 1 over T1. So basically T1 is the temperature at which we're measuring the first vapor pressure, P1. T2 is the temperature at which we're measuring the second vapor pressure, P2, and these still have the same definition. Now this is the form of the equation that your book uses, so that's why I'm using it. There's another form of this equation where basically you either invert the natural log or you invert the two temperature terms and put a negative sign out front of here. So there's two forms of the equation. If you have an older version of the textbook or a different version, you might see a minus sign out front, and these two switch. They're mathematically equivalent, and this is the one that your book uses, so I'll stick with it. Okay? All right, so that's the more useful form, which involves comparing the vapor pressure at two temperatures. So what we can do experimentally, if we want to measure then the enthalpy of vaporization, we want to measure this constant C, we look at linear relationships. So if we put the natural log of the vapor pressure on the x-axis, or sorry, the y-axis, so that's going to be our y variable, is natural log of vapor pressure, and we're going to measure that as a function of 1 over the temperature. So on the x-axis is going to be the inverse of the temperature. From this equation here, this is y, this is x, so y equals mx plus b, linear form of an equation in this case. So our slope is going to be minus delta H over R, and our intercept is going to be equal to that constant C that we have in this form of the equation. Which again, we're not really going to usually use this form of the equation, but we can measure that constant C if we look at the dependence of the vapor pressure on the temperature. So if we compare two different substances, water might look something like this. Again, this is qualitative. So remember, the slope of this is related to the vaporization enthalpy. We'll talk about this in more detail in a second, but basically the vaporization enthalpy depends on the intermolecular forces. So water has a lot of hydrogen bonding interactions, so the molecules are held strongly to the surface, and you have a low vapor pressure and a pretty high vaporization enthalpy. It takes a lot of energy to pull those molecules off of the surface. Now if we compare that to another liquid, diethyl ether, another common organic solvent that you'll use if you take organic chemistry lab probably. I'll do that in red. The structure of this is CH3, CH2, OCH2, CH3. So this is a polar liquid. It has carbon-oxygen bonds, so it's polar, but it doesn't have any OH bonds, so it does not have hydrogen bonding. So this has weaker intermolecular forces. We would expect it to have a smaller vaporization enthalpy. It's easier to remove the molecules and put them into the gas phase. So for diethyl ether, it would be a shallower slope like this. All right, so the point being, if we measure vapor pressure as a function of temperature and plot it in this way, with the natural log of the vapor pressure on the y-axis, the inverse of the temperature on the x-axis, the slope of these lines relates to the vaporization enthalpy, and that's how we can measure it in real systems. Okay? All right, so let's look at some example problems of how we can use this equation. So the first one is just a straightforward application of it. So let's say, go back to that substance diethyl ether that we just talked about. It has a delta H of vaporization of 29.1 kilojoules per mole and a vapor pressure of 0.703 atmospheres at room temperature 25 Celsius. What is this vapor pressure if we heat it up all the way to 95 degrees Celsius? Okay, so we're going to use this equation to calculate the new vapor pressure. Natural log of P1 over P2 is equal to the enthalpy of vaporization divided by R times 1 over T2 minus 1 over T1. So most of these terms are given to us in the problem. T1 is 298 Kelvin. The temperatures have to be in Kelvin for this equation, so this is another case where don't forget that. Anytime we're doing absolute temperatures, they have to be in Kelvin for these types of problems. So T1 is 298 K. T2 is going to be 95 Celsius. We add 273 to that. That's 368 Kelvin. So just converting the two temperatures into Kelvin. And then the initial vapor pressure, P1, as we'll call it, is 0.703. All right, so it's important when doing these problems not to flip the terms with each other. So we're given the vapor pressure is 0.703 atmospheres at 25 Celsius. So if we're calling 25 Celsius T1, that means P1 is the 0.703. We can, which one we call P1, which one we call P2 is kind of arbitrary, but they have to be matched up with the correct temperature when we set up the equation. So now we just start putting numbers in. So the natural log of 0.703 atmospheres divided by P2, which is what we're solving for. We put the delta H of vaporization over R, and here again is where we have to be careful with units. So we're going to use this form of R, 8.314. That's joules per k mole. That value of R is also on your constant sheet, so you don't have to worry about memorizing it, but that's the alternative value of the universal gas constant in terms of joules. Now, if this denominator is in terms of joules, that means our numerator, delta H of vaporization, also needs to be in joules. So we're given that it's 29.1 kilojoules. Most enthalpies of vaporization are in terms of kilojoules. We have to convert that to joules and put it up here to make sure the units work out. So we're going to put that in as 29,100 joules. Just multiply and that's joules per mole, multiply the number by 1,000. All right, so because we want joules to cancel out, moles to cancel out as well. And then finally we have our temperature terms, which are going to be 1 over T2, which is 368 Kelvin, minus 1 over T1, which is 298. So if we multiply out this whole right side of the equation here, it's just a bunch of numbers now, there's no unknowns on the right side. If we multiply that out, we get minus 2.234. So I'm going to walk you through the algebra on this one just because it's the first time we've seen this type of problem. If you haven't noticed, this is not an algebra class, but we'll go through this one. So we take, the way we do this is we take we take the exponential of both sides. So if we want to get rid of the natural log, that's going to be equal to e raised to that power minus 2.234. All right, so exponents undo natural logs, so we take e to that power minus 2.234. That gets rid of this natural log, and that's going to be equal to 0.107. So when we solve for P2, now it's just a simple algebra problem, we get 6.56 atmospheres. All right, so there's a pretty big effect of the vapor pressure on temperature, especially when you have a low vaporization enthalpy like we do here. So at room temperature, it's 703.703 atmospheres. If we raise it up to 95, just below the boiling point of water, the vapor pressure skyrockets all the way up to 6.56 atmospheres. All right, so it's just using this equation to solve for one particular unknown, which in this case was the vapor pressure. All right, what we'll close with is there's one other way that we can use this equation. But first, let's talk about the relationship between intermolecular forces and vapor pressure. All right, so other types of things we'll have to understand are the relationship between these things. And we kind of already mentioned this. So stronger intermolecular forces correlates with a lower vapor pressure. All right, and that's because, remember, that vapor pressure is caused by molecules escaping the surface. If we have stronger forces holding those molecules to the surface, we'd expect to have less molecules escaping and a smaller vapor pressure. Okay, so vapor pressure requires molecules to leave the surface, so the stronger the forces, the more molecules that are going to be held in the liquid phase. But then if we want to look at the effect of intermolecular forces on vaporization enthalpy, in this case there's a direct relationship. Stronger intermolecular forces correlates with a larger enthalpy of vaporization. And this is because more energy is required to break those intermolecular forces and have the molecules leave into the gas phase. All right, so as we said, if we're comparing two liquids, we can look at the relative strength of the intermolecular forces. Remember that London dispersion forces are the weakest, then dipole-dipole, then hydrogen bonding interactions. And depending on the strength of the intermolecular forces that exist for a particular liquid, that's going to relate to both the vapor pressure and the vaporization enthalpy, which are inversely related. Something that has a lower vapor pressure tends to have a higher enthalpy of vaporization and vice versa. All right, so that's just something also to keep in mind kind of conceptually. Now, the last thing we'll talk about today are some more precise definitions of phase changes, which will lead into the stuff we're going to do next time, and then also is going to allow us to look at that last equation that we talked about in one different way. All right, so when we talked about boiling point, we introduced it at the beginning of this chapter as the temperature at which the liquid molecules convert into the gas phase. Now, a more precise definition of boiling point is the temperature at which the vapor pressure is equal to the atmospheric pressure. Okay, so the temperature at which the vapor pressure is equal to the atmospheric pressure is what we call the boiling point. So we start with a liquid below the boiling point. We start heating it up. The vapor pressure is going to rise steadily, and then once we get to the boiling point, that's when the vapor pressure is equal to the atmospheric pressure, and the liquid is going to start boiling, where you're going to have net escape of the molecules into the gas phase at that point. The associated enthalpy of vaporization, we already talked about that today. So every phase change has an enthalpy associated with it. We call that enthalpy of vaporization. Now the other phase change temperatures also have more precise definitions. So melting point is kind of a weird one, a weird definition. Remember that this is the temperature at which solid and liquid interconverts, but the more precise definition in terms of vapor pressure is it's the temperature at which the vapor pressure of the solid and the liquid phases are equal. So even solids have some vapor pressure, usually much lower than liquids. But the melting point is the temperature at which the vapor pressures of the solid and liquid phases are equal. All right, so at that temperature, you're going to start converting liquid into solid, or they're going to be both existing at the same time. Okay, so that's the precise definition of melting point. And then the enthalpy for melting is called the enthalpy of fusion. Abbreviated as delta H, FUS, for fusion. This refers to melting, so it's going to be also a positive number. Okay? All right, so that's the enthalpy of fusion. We'll talk in more detail about that next time. And then finally, if we want to have what's called the normal melting point or the normal boiling point, that's when the surrounding pressure is 1 atmosphere. So that means for the normal boiling point, that's when the atmospheric pressure is equal to 1 atmosphere. Or sorry, the vapor pressure is equal to 1 atmosphere, which is also equal to the atmospheric pressure. So when we say the normal boiling point of water is 100 degrees Celsius, that means at 100 degrees Celsius, the vapor pressure of water is exactly 1 atmosphere. So if you know the normal boiling point of a substance, you know that at that temperature, the vapor pressure equals 1 atmosphere. So whenever the boiling points of a substance are tabulated, that refers to the situation where the surrounding pressure is 1 atmosphere, which means once the vapor pressure equals that 1 atmosphere, you have boiling occurring. All right, so that leads us down to one last example problem, which is another way we can use that equation that we talked about earlier for vapor pressure. So let's say we have a certain liquid that has an enthalpy of vaporization of 35.5 kilojoules and a normal boiling point of 122 degrees Celsius. What is this boiling point at the top of Pikes Peak, where the barometric pressure is 457 millimeters of mercury? Pikes Peak is in Colorado. It's quite a sight to behold, but as we know, the air pressure, the atmospheric pressure decreases as you go higher and higher in altitude, which of course leads to altitude sickness and things of that sort. So if we go to the top of this 14,000 foot mountain, the atmospheric pressure is 457 millimeters of mercury. I don't remember if that's the actual number or a made up number, but let's assume that it's true. And so how is that going to affect the boiling point when we go up to the top of Pikes Peak? So the boiling point of a substance depends on the surrounding atmospheric pressure, so let's try to calculate it in this case. So we still use that same equation, the ratio of the two pressures, vaporization enthalpy divided by R, and then 1 over T2 minus 1 over T1. All right, we're starting here. And so we have to look at the problem and see what information we're given. The enthalpy of vaporization is given. This is going to be our T1, 122 degrees Celsius. That's the normal boiling point. And remember, at T1, which is the normal boiling point, that means the the vapor pressure P1 is equal to 1 atmosphere. So whenever you're given the normal boiling point of a substance, that gives you a pair of temperatures and pressures. The temperature is 122 in this case, and that means the pressure at that temperature, the vapor pressure at that temperature, is exactly 1 atmosphere. We have our second pressure here, which is 457 millimeters, and so we're just going to solve for T2, which is our unknown. So we take the ratio of the two pressures. P1 is 1 atmosphere, which is 760 millimeters. We have to put them in the same unit, so they're a ratio. P2 is the second pressure, which is the pressure associated with the unknown boiling points, 457, that's given to us. And that's going to equal the enthalpy of vaporization divided by R. We have to convert that into joules per mole by multiplying by 1,000. So 35,500 joules per mole. Many of you will forget to convert units because many of you don't write units when you're doing problems. And then you'll come ask me why you got it wrong, and I'll show you they didn't convert units, and then you'll possibly do it again on the test. So try to remember to do that. Let's get in the habit. So we don't break the cycle. That's the goal here. All right, so we're going to put the vaporization enthalpy divided by R. We have our unknown T2, and then T1 is the normal boiling point associated with 1 atmosphere vapor pressure, 122 Celsius, which we convert to 395 Kelvin. Okay? So that's the equation in this case. So we work out the numbers. We get 0.5086 is equal to 4269.9 divided by T2 minus 10.81. So that's where the algebra works out to. Just simplifying things, we just take this, we multiply, we factor across, and then that means T2 is 377 Kelvin, which is equal to 104 degrees Celsius if we want to put it in the same units. Alright, so basically by climbing to the top of this mountain, the boiling point of this substance reduces by almost 20 degrees Celsius, And that's why if you've ever read the instructions on the back of a food label that involves boiling water, it says if you're at a high altitude, boil it for longer because the boiling point of water is lower at high altitudes. And we can use this equation to calculate what it would be for a given atmospheric pressure. All right, if everything goes as planned, we'll finish up everything on Friday. Last call if you have anything you want me to go over on next Monday. We should have some time to cover whatever you want, so please send that to me in advance if you want me to include it.